So the HorizonCube is a dense set of correlated stratigraphic surfaces, three-dimensional surfaces that are assigned a relative geologic age, and you can use this as input for a wide range of applications. This was originally developed as a part of the plugin for the sequence stratigraphy. This was the chronostratigraphy application, but now it is fully 3D, and we've realized that it can be applied in so many other places, so we've separated it out into its own plugin, and the sequence stratigraphy can be added on as a secondary plugin to this later on. Now the applications of the HorizonCube, as I said, can be applied to quite a variety of geology or geophysics. You can, we will show you today how to create the HorizonCube. I will introduce a bit of the background of what you need for creating the HorizonCube and a few of the shortcuts that you may need to learn. Arnaud will introduce some advanced applications dealing with geomodeling and inversion. And Paul will finish up by showing us about how you can use the sequence stratigraphy plugin and the wall correlation panel. So we'll go ahead and get started, and I'll give you a brief introduction on how to create a HorizonCube, and then we'll go into OpendTect and I'll show you how to do it. Now for creating your HorizonCube, there are multiple models that you could use. You can assign different models per package, so depending upon how many horizons you'd like to use, you can get an individual package in between two horizons. Now these models that you can use, you have the model-driven, which one example is the linear interpolation, which is basically proportionally slicing in between the two horizons. You can also have parallel to upper or parallel to lower. So if you have the horizon that you see here is parallel to the upper and it truncates as it hits the lower one, and vice versa over here. And you also have the data-driven model, which it uses the bounding surfaces as a top and a bottom, but it uses the steering cube to look at the dip and the azimuth of each trace, and it will drive the chronostratigraphy, or the HorizonCube, the horizons, along the seismic in that manner. Now when you create a HorizonCube, you need to think of a few things. First of all, you must have your bounding horizons. You need to have at least two horizons, but as I said before, you can use you can use multiple horizons. So if you have 5 horizons, then you end up having a package in between each of those horizons. Additionally, you can incorporate faults. If you have faults in your data, or if you have fault blocks, you can create the horizons in between all those faults, so you have to incorporate those. And if you do want to use the data-driven method, then you incorporate your dip steering. And this is the example that we'll be seeing today. Now when it comes to the bounding horizons, it's important that you think of a few things. First of all, you can use existing horizons. You simply import them into OpendTect, or you can map them in OpendTect through two popular manners. The first one is our traditional amplitude and similarity auto tracker, which tracks the horizons in a stepwise manner. And there's also the new dip steering horizon tracking, which is available as part of the HorizonCube plugin, and we'll give an example of this today. It's a really powerful new tool, and I think everybody will be very pleased when they see how easily it works. Now if you do have existing horizons and you have faults, you need to trim your horizons at faults. And if you don't have horizons and you want to track them using the HorizonCube with the dip steering, all you have to do is assign a fault, and you can automatically track your dip-steered horizons around the faults. But as I was saying, if you have existing horizons, you can trim them at the faults using a tool available in the HorizonCube. Now this is an example of a horizon where you see the fault is clearly going through right here, but it's connected. Now here's an example of that horizon that's trimmed at the fault. So you see it is completely cut, It's not connected at all when viewed at section, and it's very nicely going through here. Now these were both tracked using the dip steered option through the HorizonCube. Now here's an example of what a HorizonCube looks like when you assign the fault both inside the HorizonCube and when you have the horizon trimmed at the fault. Now this option is using a horizon that is not trimmed, but it's telling the HorizonCube it wants you to trim at the faults. So you see that some places you do have the HorizonCube trim, but at some places it still connects over the faults. So when you compare these two, it's clear how important trimming the horizons at the faults actually is. Now the dip steering, as I was saying with the data-driven model, you need to incorporate the dip steering. A steering cube is very, very important part of creating your HorizonCube. And when you think about creating your steering for this, steering, when it's created for different purposes, you will filter more in the vertical direction, or you may filter more laterally. So you need to think of your application. And in this application, we are looking at horizons. So we want to let me go back. We want to look at the horizons laterally. So we want to not filter so much in the vertical direction, or we may smear. Now, for a more detailed introduction to creating your dip steering, there's a Steering Cube webinar on our website at dgbes.com. So you can look on there and it will describe how to create the optimal steering for different situations. And it does give you an option for the sequence stratigraphy, which is an application of the HorizonCube. Now the degree of filtering is something to consider. You want to do as little filtering as possible on the steering that you use to create your HorizonCube. Now if your data does need a large amount of filtering, make sure you do it to the data, to the overall project, and not to the steering for the HorizonCube. If you precondition the seismic data and use as little steering as possible, or as little filtering as possible on the steering for the HorizonCube, you're much better off in your product. Now this is showing one of the windows for the advanced options that are available in the HorizonCube. And these will be discussed in more detail by Arnaud and Paul later on. But the continuous events option and the truncated events option, basically the continuous events are good for basin modeling, and the truncated events are good for viewing in the Wheeler domain. So and these can also be changed later on. If you create a continuous HorizonCube, you can truncate it and vice versa. And this is a new option available in the HorizonCube, the min-max starting position. What this does is it starts at the peaks and the troughs on your line, whereas the fixed spacing starts at a set number. Now the min-max option is good for a layer cake setting. It starts at the extrema and it tracks much better there. So it's a good option if you have a pretty straightforward, pretty simple data set. Now the fixed spacing option, as I said, it will start at whatever spacing you specify. These are the default values in there. And what it's saying is it will start a seed every 8 milliseconds, and then if the holes become larger than 16 milliseconds by 100 traces, it will insert a new horizon. So here we see these are our seeds. These are our starting positions that are 8 milliseconds apart, and as it starts tracking following the dip, you see some horizons get further apart and some get a lot closer together. So if this one ends up being more than 16 milliseconds apart and 100 traces apart, then a new horizon would be inserted. And another option that's now available with the HorizonCube are iterations. This is actually a really great option. You can start off by doing one iteration. It will run very fast. You can get a good idea of what things will look like, and you can always go and add more iterations later. And now it is time to start our demo. So here we are in OpendTect. We're just going to look at a simple survey. This is the F3 survey. It's a 3D survey in the North Sea. This is available for download on our Open Seismic repository at our website, opendtect.org/OSR. Now here I'm displaying two inlines and one fault. So as I was saying, with our HorizonCube, there are certain things you need. You need your bounding horizons. If you have faults, you have to incorporate your faults, and steering if you want to do a data-driven. So I'm displaying here the steering for this data set, and basically everything that's in green is dipping towards the shore, everything that's in blue is dipping towards the basin. And so now we'll go ahead and start tracking our horizon. And if we need to track around this fault, then you would think that you would want to place seeds on either side of the fault. But I'll show you why that should not be done. So if we go to Processing, HorizonCube, Create Horizons from Steering Cube, this dialog box opens up, and it tells you to pick one seed per horizon. However, if you add faults, it tells you pick one seed per fault block. Now if we look at this and we pick one seed on either side of this, it will grow out in this direction. But if we pick one seed out here, it will grow organically around the fault, and you'll get a seamless transition. And you only need to use one seed. So one seed in this entire survey, and you'll be able to track our horizon. And we're not going to do one of these easy ones. We're going to go ahead and pick one down here. So we'll start off. We pick our steering. We pick our fault. And now we pick a seed. I'll go ahead and turn this here so we can see it as it grows. And now we just click Apply. Now this is, I'm running on a laptop right now, so this is just going to take a few seconds, and then we'll end up having a full 3D horizon that was calculated by following the dip from our steering cube. And just think about how much time you end up spending tracking your horizons and how much quicker it goes when you do something like this, and you get a much more accurate horizon. Look at that. Go ahead and dismiss this. Well, let's go ahead and turn off the lines. Just zoom in. Get a nice look at that. Look at that detail. All this from one seed. And now, let's go ahead and turn off our fault. And you see that we're cut at the horizon here. Now yes, you do see little connecting pieces, but that's simply visualization. If you zoom in, they go away, and you see that it really is not connected. So now we have a beautiful horizon on a very difficult portion, and we could use this as input for our HorizonCube. However, what we want to look at is this nice complex right here. So we'll turn off this horizon, and we'll go ahead and turn on some of the other horizons that were calculated in the same way. So that's our bottom, that's our top, and we'll even include an intermediate horizon. And I'm going to go ahead and display these only at section, and then we'll just look right here. So now we'll go to create our HorizonCube, because we have our steering, we have our bounding horizons, and we have our fault. So now I'll go to Processing, HorizonCube, Create, 3D. So it opens up a dialog box where you basically just start from top to bottom. So we will read the horizons that we want to use. So we go pick bottom, middle, and top. Okay. And you see that we do have separate packages here now. We have two packages, and there are options with these packages. So in between the top and the middle horizon, we can select what kind of mode we want to use for calculating our HorizonCube. And we can do the proportional, which is the straddle slicing, or parallel to upper or parallel to lower. but we'll go ahead and use the data-driven option. So now we've selected this, and if we didn't change anything else, it would use the default settings. But we want to go ahead and go in and do the options. So we need to select our steering cube, and we have options for our starting position. So as I showed you in the PowerPoint, where you can automatically start every 8 milliseconds apart, or you can set that differently, you can specify where in the data set you would like to start the calculations, and this can make a big difference. So you do want to play around with this to optimize your steering cube. Now you can start at the thickest point at the center, or the inline center and the thickest point. So now we're going to actually use the user-defined option, which is even more specific. So say you have an exact inline crossline position that you want to start at. Well, let's do that one. And then you can also look at your advanced options. So we'll go ahead and by default create a continuous event, fixed spacing. You could even make this very specific, get it really, really detailed. And so now we've done all these changes, and if we deselect this, then it will only apply it to this one package. But let's say you have 5 different packages and you want to apply the same settings to all, just leave that checked, and then now it applies it to every package. So let's go ahead and pick our fault. You can also do a sub-volume if you don't want to run the whole volume. If you just want to do a particular area, you can limit by your inline and your crossline ranges. And then we can give it a name. And this button is a great addition. Rather than running your HorizonCube and then finding out later that you made some silly mistake, you can press the Analyze button, and it will take all of the parameters that you've set out, and it will do a quick test to see if it would even work. And as you see here, I get a response saying that everything failed. None of my packages were able to process. So if I go and I look at the individual packages, it tells me, first of all, that it failed, but it tells me what the error is. I have a problem with my start position. I started it at inline 250 and crossline 1100, but it's telling me it's outside of the bounding horizons range. Well, okay, I'll dismiss this. And I go and I look at this, okay. Oh, well, look here. When I did my sub-selection, I put it at 1,000. Why don't we go ahead and change that, put it above. So we're starting at 1,100, so make sure that goes to 1,200. We'll try it again. And now I have a positive response that both of my packages passed successfully, and now I can press go and I will get a HorizonCube that will actually work and give me good results. So let's go ahead and go to Processing, HorizonCube, Select, and we'll pick a HorizonCube that was calculated earlier, and we'll go ahead and load this now. So add HorizonCube display, and it will add it to this inline. Now, while it adds it to this inline, it's going to only be displaying it here, but this really does exist everywhere. You can load this on an inline, on a cross line, on a random line. So this is it's all displayed on the fly. So it's stored, and we can look at it anywhere we'd like. And now we can go in here and we see all of these lines. And you can get in here and you can see how nicely this goes along with our seismic data. It's using the dip steering. And so as I was saying before, if you get a result that you're not too happy with, adjust your steering parameters and you'll probably find out that you get a much better result. So we can go in here and we can start scrolling through the data, and look at that. You can see this building up. It's just beautiful. And now let's say that you see an area that you're like, you know, I'd really like to see this and see what it looks like. So here, look at that. We have one horizon that looks like it's the top of a package, why don't we see what this looks like in 3D? So we'll go to our HorizonCube tools, and as I was saying before, there are lots of options that you can do once you have created your HorizonCube. You can add more iterations, you can modify your packages. Let's say you don't like the way one package turned out and you want to take it from data-driven to striatal slicing, you can do that. But let's go ahead and extract this horizon and see what it looks like. So as you see here, we have this red line right here, right where this HorizonCube horizon is displayed. So I can pick that horizon and give it a name. And now I have a name. I can press proceed, and I can get my 3D horizon and load it. Now this, if I display sections and in full, this is that horizon directly from the HorizonCube, and this actually happens to correspond with the top of the system track. So this is something that's really it's really quite powerful in what you can do with this, because this can be put into our system track interpretation system, or it can be used in geomodeling. And I will now actually go ahead and pass this on to Arnaud, where he can talk in more detail about some of the advanced features. So Arnaud, if you will unmute yourself, I will pass you the presenter skills.
Thank you, Renee. And let me start now. I will assume that we have an HorizonCube and that has been loaded in the full survey. It has been created in the entire survey range, and I'll show you how we can use this HorizonCube in order to build geological models. And as Renee told us briefly on the starting point, when creating on the horizon, there are two kinds of HorizonCubes. We have truncated HorizonCubes and we have continuous HorizonCubes. For the workflow I'm about to show you, it is of utmost importance to have a continuous HorizonCube. If that is not the case, there is a tool here that allows you to create a continuous HorizonCube from a truncated HorizonCube. So it's a very quick translation workflow that will simply propagate all these individual patches throughout the entire survey. The aim of this process, the aim of having a continuous horizon, is that it is very important that these horizons have a throughway travel time everywhere in the survey, so that is for every seismic trace of the volume for which we want to build a model. Now the creation of the models doesn't depend only on the HorizonCube, it is also driven by the wells. So actually the wells, I have here 4 wells in this survey, will provide the target to be graded in the 3D survey. And the aim, here you see 4 impedance logs loaded right of the deviated wells. The aim of the process is to propagate these logs that are coming from the well in the survey area in order to have the same log amplitude at every sample location of the seismic survey. There are 2 main applications for doing this. You may want to do this when you create a reservoir model by propagating porosities throughout the survey, or alternatively you may want to propagate impedance values prior to running an impedance inversion. In that case, and that is what I'll show right now, you need to be able to move these log values between the wells and to compute, to estimate an impedance amplitude at every sample location of the survey. And how is it done? Well, traditionally this is done by following a very core set of horizons in the survey, 2, 3, 4 horizons. And what I will show is the main benefit we have by not using only two horizons for guiding the well logs, but by entering an horizon cube, so a very large set of horizons in the entire survey. For this horizon, you can see that I have not 2, 3, 4, 5 horizons. I have 800 horizons between these base and top horizons to perform to use in order to perform the gridding. The gridding as such is done in one specific step of the volume builder. The volume builder is this icon with 3 cubes, and we'll use one very specific step that is doing this entire workflow. It's called the HorizonCube well interpolator, and as input it will use the data I've just shown. So the HorizonCube that I've made with 2 iterations and our well logs. The well logs will be P impedance logs selected for all my wells, or for any selection of wells in the survey. Now you understand that because we are doing this gridding following the HorizonCube in this time domain survey, it is very important that the log data is actually correctly localized in the survey area. Any shift problem will result in a wrong model after the gridding of these well logs. So it is very important to make sure that the logs have been first fully prepared, edited, and secondly that the wells have been tied to the seismic survey in such a way that the log amplitudes are in front of their geometrical location, their true geometrical location in the 3D space. If you are using a depth survey, you should also mind that the depth of the seismic volume may not correspond to the actual depth of the wells. In a depth survey, you're really gridding the log with respect to the well depth and not the seismic related depth. The gridding is very simple to do. I have to enter a name for this gridding step. So what I'm doing in this step, I'm gridding acoustic impedance logs using a data-driven HorizonCube. And that is about the only thing I want to do. Well, this volume builder has a lot of more tools that we won't use for this kind of very specific application. Now this step needs to be saved in a processing setup that I'll save right now with a temporary name. Okay, so this is the name of the entire volume builder setup. Now I may go directly to batch processing if I leave this option on, process and OK, but for now I would like to apply it on the fly on a number of key inlines to have an overview of how the gridding is performing. It is very important to do if you have doubts on the synthetic to seismic well tie quality, for instance. So I've toggled off this option. I'll press OK. This will save and load save the setup on disk and load it in memory for application on that inline. And the application is to be done on inlines and crosslines in the right-click menu of these elements, using this very specific layer type, which is called a volume processing attribute layer. And as you can see, on its right click you have very few options. The main one is to select a volume builder setup, which is the one I've just created in the volume builder. Okay. Now press OK, and that will launch the computation of the impedance, the gridding of the impedance logs in 3D. That doesn't take so much time, 2-3 minutes. And once it is done, you can go back, toggle this option off, on, process and OK, and this will conduct you straight to the batch processing window, where you need to provide an output name and launch the batch processing. Now for this short demo, I will not do so much computation. I'll go straight to the output which is the following. So after batch processing, you'll get this result stored on disk. So this is your impedance logs graded using the HorizonCube. But let's wait for a minute. This is actually not the result of what I showed you. This is what you would receive in the usual case by using a proportional slicing between the top and base horizons. And as you can see, we don't have all the detail of the seismic data. The seismic reflectivity is not honored. When you use the HorizonCube, you'll go from this case, which is the standard case you all know, from this horizon-driven grading of the impedance logs. And as you can see, this is the major change you can expect by switching from a traditional grading, which is this output, to the HorizonCube grading of the well logs. And as you can see, once again, I can play with some transparency to have it partially transparent. You can see that all these impedance features really follows very accurately the seismic reflectivity. They are really in line with your seismic layers, and as a result, you'll have a very detailed geological model out of this workflow. Now what you see in the deep part is below the base horizons. I've simply used a parallel to base model, which is why it is not following the reflectivity below the base horizon. And now I switch back to the standard view. Now you can do this really for any amplitude values that you have loaded as a log along your wells. And as I've done it was with impedance data, this is the graded porosity volume only between the top and base horizon of this HorizonCube. Actually, these grading steps are to be found here during grading. You may want to either do no vertical extension of the graded volume, in which case you'll get an HorizonCube like this, limited bounded by the HorizonCube geometry, or you may want to grade the data parallel to the top and base horizon, in which case you'll receive a volume where you have data everywhere, like in this case, in this example. Okay. This initial model, this initial acoustic impedance model, is most often not what people will use for running an impedance inversion, because it still has all the frequency detail of the well logs up to the seismic sampling rate. And most often when creating such an initial model, interpreters tend to apply a low-pass filter that will start at the frequency where the seismic spectrum that I'm displaying right now starts. So that is at 10, 15 Hz. So in order to have a low-pass filtered version of this output, you simply need to take the output volume and to run a frequency filter attribute on the graded impedance logs. So it is attribute type is frequency filter, will apply a low-pass FFT filtering 10 to 15 Hz. And because we are grading a real rock property, we will not want to do any window tapering in the time domain, but only in the frequency domain. And this is our low-pass impedance model attribute, for which I've just provided a name. This is now loading the attribute, and we can apply this low-pass impedance filtering on that inline as compared to it. And if you have some uncertainty on the amount of low-pass filtering, you can simply evaluate the maximum frequency by entering any value and any step in order to have an overview of how much frequency filtering you want to do. But as I said previously, it's mainly guided by the amount of frequencies and the frequency bandwidths of the seismic data. So most often the frequency filtering will be somewhere between 10, 20, 30 Hz. And that is, so this is the output for 10, 15, 25, 30, 35, 40, right, and so on. But as you can see, even though we diminish the level of detail up to 30 Hz, we still have a very good following of the seismic reflectivities, and we still have all the benefits of having gridded the impedance logs using the HorizonCube as a guide. And this is ends the presentation of how to create geological models using the HorizonCube in OpendTect. I now hand over the presentation to Paul Groot that will give you an overview of the well condition panel and sequence stratigraphy analysis.
Okay, thank you, Arnaud. What I would like to do is show you some of the sequence stratigraphic interpretation capabilities we have, including the new well correlation panel. And when we talk about sequence stratigraphy, there's always immediately an enormous confusion about what you mean in terms of where is my sequence boundary, where is my system tract, what is the base level, and so what I would like to do first is to give a crash course of like 10 minutes on the very basic principles that we will apply before we go into the sequence stratigraphic interpretation. So this will not be a full course, it will just be focusing on some basic terminology just so that we know that we are talking the same language. Basically what we are doing in our SIS application is that we are interpreting geologic time, and if we look at a single reflector in a seismic data set, then that is a first approximation of geologic time. So if I'm capable of mapping all the reflections in a seismic volume, and basically I'm looking at geologic time, or as we used to call it in SIS, the ground stratigraphy. With that, we can reconstruct the depositional sequence. We can learn a lot by just sliding the ground stratigraphy, adding and removing more geologic time. We can also use these horizons, these ground stratigraphic events, to flatten our data. And such a flattening is called a Wheeler transformation. On the left we see a two-dimensional Wheeler transform, and basically the vertical axis here represents geologic time, in our case relative geologic time. What we can see in such an image is how far each of my layers has been preserved. And I can also see how the depositional center shifts over geologic time, first going basinwards, then going landwards, then going basinwards. I see that I have gaps in my data. These gaps correspond either to erosions or non-deposition, or they correspond to condensed sections. So this type of display is very handy for, that's helping me when I do a system tracts interpretation. And I will define system tracts later on, but it's basically how we want to cut up our sequence into logical packages. And this is very often the goal of the sequence stratigraphic interpretation. We want to find the potentially good areas where we may have reservoir sands kept by seals. So this is the ideal tool for stratigraphic trapping. So let's define a few basic definitions. If we talk about sequence stratigraphy people very often talk about sea level rising and falling, but basically that is not all of it. If you talk about the sea level, there are different sea levels. There's the eustatic sea level, which is measured relative to the center of the Earth, and then there's also the local tectonics, which can also rise or fall. And together, eustatic sea level plus tectonics gives me the relative sea level curve. Now if I add two more components, the energy flux, that is the waves and the currents, and the sediment supply, I can define the base level. And the base level is one of these virtual planes that are really very confusing to many people. So let me try to define this. We're looking at a simple situation where there's no sea level change and no subsidence or uplift. We have wave energy and we have a sediment supply. If these two are in balance, then the base level is the seafloor. There's no accommodation space. This system is static. Nothing will change. Now the next situation, we have more sediment supply than wave energy. And now our base level is actually located above the seafloor. There's a positive accommodation space that will be filled by sediments. In the third situation, the wave energy is larger than the sediment supply, and now my base level is actually located below the seafloor, and this is the maximum surface to which this system can erode. And we have a negative accommodation and space. Now these base level rises and falling, and the sediment supply and the currents and the wave energy give rise to different type of packages. We distinguish two basic packages, that is a transgression and a regression. The definition of a transgression is that it is a landward shoreline and phase shift, whilst the regression is a seaward shoreline and phase shift. So basically these are the components that we can play with. We have eustatic sea level rises and falling. We have tectonics, together they make the relative sea level rise and fall. We have the energy flux, and we have the sedimentation, the sediment supply. All these components can change over geologic time, and how they change is what is eventually what we end up in terms of sedimentary packages, the type of reflection patterns that we will see in the seismic and that we will interpret. The type of packages that we might distinguish, the architectures are like this. We can see progradations, that is building forward, aggradations, building upwards, building or stepping backwards, retrogradation, and incisions. These are the four depositional architectures that we will see in our specific setting, which is the data set that we will be analyzing, the F3, which is a passive margin setting, basically a deltaic setting where we have all these type of components. Now let's see where these type of packages are actually occurring if we look at just one cycle of base level change, one rise and one fall. Even more important than base level rising and falling is how fast the base level is changing. So if I differentiate this curve, I get the rate of the base level change. And if I put in now a constant sedimentation rate, and I start here, then this is my initial situation. Now I'm moving through geologic time, and in this case we have a sedimentation rate that is larger than the rate of the base level change. The pattern that emerges is one of normal regression. You see aggradation building upwards and progradation building outwards. The process is that the base level is rising, but the consumption of accommodation space by sedimentation exceeds the creation of accommodation space by the base level rise. That continues all the way until here. Here a new situation starts. You're still building upwards, base level is still rising, but now the sedimentation rate is smaller than the rate of base level change. And the pattern that emerges is one that belongs to a transgression, backstepping, or retrogradation. So it's characterized by aggradation and retrogradation. The base level is rising, more accommodation space is created than is consumed by sedimentation. All the way until this point, and here we are getting back in a familiar situation. Sedimentation rate is larger than the rate of base level change. And that continues until here. Now we have seen this package before. This is again a normal regression. So the normal regression, it emerges, or it originates in two parts of this base level cycle. One in the lower end when we started, and one in the upper end at the top of the base level rise. From here onwards, again, we have a different situation. We now have a base level falling, a decrease of accommodation space, and this is called a forced regression. It's characterized by an incision, so we have an unconformity, but also a progradation. The base level is falling, decreasing accommodation space, forcing the system to prograde, all the way until this point. So basically we have transgressions and regressions. The transgression and the normal regressions, they originate when we have the base level rising, and we have the forced regression when the base level is falling. Now, how do we then do a system tracts interpretation? We can look at rising and falling again, but it's more logical to cut up the curve in terms of transgressions and regressions. And there are remarks on specific points that are of interest in this curve, and then we can cut up this cycle in terms of system tracts. In this case, this is defined as a low stand in yellow, then we have the transgression, we have the high stand. So these two have similar packages, both normal regressions. And then we have the falling stage system tracts in the area where we have the base level falling. Okay, now that is just one way of cutting up your base level curve. And unfortunately there are many different ways of cutting up the base level curves. This depends on the type of model that you are using. That in itself depends again on what company you're working for, or what setting you're working for, or how you have been trained. The way we have just cut up this curve is what is called depositional sequence number 4, as defined by Hunt and Tucker and Plint and Nummendahl. And it divides the curve as we just did, and it puts the sequence boundary at the top of the falling stage system tracts. The other depositional sequence models are also used quite often in seismic interpretation. The genetic sequence is used mainly in log interpretation, and the TR sequence model is very often used in outcrop studies. So this is something you have to be aware of. There are different models, and people will put sequence boundaries at different positions, and also the naming conventions will be different. So if we do a system tracts interpretation, especially in the type of setting that we will be showing, then basically we are looking for these type of patterns. And if we see these patterns, then the first thing we do is we make a decision. Are we talking about a regression or a transgression? So if it is indeed backstepping, retrogradation, and building upwards, aggradation, we're finished. We can call this a transgressive system tract. That is over and done. But if we have a regression, then it can still be a normal regression or a forced regression. So we look at the top part and we look whether it's cut off, whether we have incisions. If so, we're dealing with a forced regression. If it's not cut off, but we see this building upwards, aggradation, then it's a normal regression. And then we still have to decide, is it a low stand or a high stand? Now that depends on the position where we find this package. If the package is on the landward position and below the subaerial unconformity, we call it high stand. and if it's located at the seaward position and above the subaerial uniformity, it's a low stand. Now we're also looking at well data, and what I will be showing later on is also the well correlation panel. And then of course we're looking at a completely different type of pattern. We're looking at log patterns, and mainly the gamma ray type of changes. So if we look at a transgression, constant sediment supply, and we're drilling over here, and this package, we will see that since the base level is rising, energy is decreasing, the sediments will be finer and finer. We have a fining upwards sequence, and it will be topped by a maximum flooding surface. But if we look at a situation like this, where we have a forced regression, the base level is falling, we have these erosional features, we're drilling over here, then basically we're looking at a gamma ray response that is looking as a coarsening upwards, and because this is the top of our forced regression, the sequence boundary will be put on that position. So these are the type of things that we will have to look at and combine that with the patterns that we see in the seismic, when we do a consistent interpretation of well logs and seismic. I know Renee already mentioned that we have two different types of horizon cubes. We have the continuous horizon cube and the truncated horizon cube. If I make a Wheeler transform of the continuous horizon cube, then it doesn't really look very good, because it's continuous everywhere. It's just a big spectrum of seismic or colors in this case. The seismic itself looks like this, and we see these huge stretched areas, and that is where we have a very dense set of horizons. Now, in that case, if we want to do sequence stratigraphic interpretation, it is better to work with a truncated horizon. And as Arnaud and Renee already mentioned, we can go from continuous to truncated and backwards using the new tools under the HorizonCube menu. If we now truncate it, we are basically filtering the density of the HorizonCube. When we have a lot of horizons, we can just remove them, and the output now looks something like this, and that is more in line with the Wheeler domain that we can use for interpretation, because I see my depositional trends coming back. I can use that for the interpretation of my system tracks, and I can also see where they have gaps, erosions, non-deposition, condensed sections, and so on. So let me now actually go and show some of the actual interpretation in OpendTect. So we're now using the sys module, and I have one line in front of me with a truncated horizon cube, and in the bottom part we have the Wheeler transform of this seismic. Over here we have the sys interpretation module, and I will shift that a little bit to the right so that I can see what is going on if I use my slider in here to do my system tracks interpretation. Now basically what I'm looking for in both domains simultaneously is changes in the sedimentary package. So if I move my slider, I will add more geologic timelines, and we see that initially all the way until roughly here we have a similar type of stacking pattern, and from here onwards it starts to change. So I will insert a boundary here, and I now right click on this column and I assign what I think it is. Now in this case I see that my stacking pattern is towards the right. The right in this case is the land, marine is on the left. So I will call this a transgressive systems tract. If I display the transgressive system tracts here, then basically there we are. This is our first package. As I did this, you can see the system has built-in intelligence. It calls the top of this bounding system tract is a maximum flooding surface, and it knows that the base level must be rising because it is a transgression. Now, in this case, I'm using this depositional sequence number 4, but if you want to cut your base level curves in any different way, or you want to build your own model, then this is all possible within the SYS module. It's really up to you how you want to do your interpretation. Okay, now we add again more geologic timelines, and we're looking again for changes in the sedimentation package, and I think there's another boundary maybe over here. I set it, and I have to assign something. Now this to me is a normal regression. I see building upwards and I see building outwards, so aggradation and progradation. So it's a normal regression. That means that I now have to make a decision. Is this a low stand or is it a high stand? If we look at the Wheeler domain, then we see that there's a huge gap above this this particular sequence. That gap is huge erosion, and we also can see that here if we would slide more units, the top of this unit is really an enormous erosion here. We have blue, very old units on top of redder units in this color scheme. So basically there is an unconformity on top. That means that this must be called a high stand. Oops, that's one too many. I should have inserted the boundary here. And this is my high stand. And this I will assign something else. So let me switch off my system tracks. Continue here. Now again we see a different type of pattern. And basically these are interpreted as slumps, turbidites, that is characteristic for a falling stage, a forced regression. So here I should insert a new boundary and assign that this is my falling stage. And in this way I can build up this entire sequence and do my interpretation. The end result of this looks more or less like this. So we have, in this particular case, transgression, high stand, falling stage, low stand, not a high stand, not a falling stage, and then a transgression. Now, as I said, or maybe I have not said it before, but in this interpretation, all these bounding surfaces I can basically save as horizons in my system. And these horizons I can then use again for further interpretation. For example, I've done that here. I've saved the top and the bottom of the falling stage systems tract as being an interesting system tract, because it could be characterized with turbidites, and these turbidites could be potential reservoir sands, and therefore I wanted to see what is the actual thickness of the turbiditic sequence, the falling stage sequence. So I saved both the top and the bottom and created an isopack of the falling stage system tract. And this is just one of the things that you can do. I can now go in and actually create a body from this. Would just interpret a polygon around it and create the body of the thickest units of interest. So this is basically the type of interpretation that you can do with this system tract interpretation. It's really understanding your system, trying to find the stratigraphic traps, and that is the SYS module, which now with the new HorizonCube is for the first time possible to do this in 3 dimensions. The next thing I would like to show is the new well correlation panel. So What we have here is a random line that we have created through these 4 wells. And I've saved this random line as a 2D seismic section. So once I've done that, I can go in here, click on this icon and pop up the well correlation panel. And that panel looks like this. So I've zoomed in already here a little bit, and I've displayed here 3 out of the 4 wells. The 4th one is more to the right. And basically this tool has been designed to pick and QC well markers so that I can build a stratigraphic framework that is really consistent not only with my well data but also with my seismic correlations. And the correlations, I'm using again the HorizonCube to guide me and to help me go from one particular unit in a well to any other unit. So I can really go in very great detail and see how the specific log response or unit that I'm interested in should be correlated across these wells. Now for this we had to develop also a stratigraphic framework, and basically the user can build up its own geologic model, stratigraphic framework, where you can define well markers. You can also define regional well markers. The regional markers are the ones that you can map on the seismic, and by connecting these two we now have a connection between seismic horizons and well markers and well logs. In this particular case we can see, for example, that I'm looking here at a well marker FS11. You can see that in the lower left corner it's displayed, and it has been picked on this marked break in the gamma ray response. I follow the seismic and I see it is correlated over here, but it is not being picked at the right position here. It's been picked over at this position, while I definitely would have liked to pick it lower. So what I can do now is I could go in and just re-pick this marker to a position where it now fits my seismic correlations and my well log responses. That is the last thing I wanted to show on the well correlation panel. So I'd like to give the control back to Venice, who can now open the session for questions.
And what I want to present you now is how you can create geological models using the HorizonCube. And I'll start, as Arnaud told us, with an HorizonCube that is one of the 2 specific kinds. It is how we can call it a continuous HorizonCube. It is continuous because every single line that you see here is an horizon that extends towards the entire survey area. If you would have made by mistake a truncated horizon, in the toolbox of the HorizonCube processing there are tools to either truncate an HorizonCube from a continuous HorizonCube or get a continuous HorizonCube from a truncated version, which is a very simple translating batch processing. Now, why do we need a continuous horizon? What we'll want to do eventually is create log data using the HorizonCube as a steering provider. And in order to be able to do such operation, we need to have a steering information, so guides on every corner of the survey. So for every seismic trace, there must be a two-way travel time for each section, for each horizon of the HorizonCube. And that is very important. That is why we need a continuous HorizonCube for this application. The quantities that will eventually will be guided by these horizons will be represented as well logs loaded along the OpendTect wells. So what you see here in the survey, I have 4 wells with impedance logs that you see displayed on the right-hand side of the well track. And the aim of creating the model geological models will be done by taking the logs from the 4 wells and interpolating them at every sample location in the survey in such a way that we get an estimated log value at that position. And so the lateral way to interconnect all the wells of the database will be to follow the seismic reflectivity as extracted by the HorizonCube processing. Now let me hide the wells. The HorizonCube, the creation of the input model will be done in this window. The volume builder setup corresponds to this icon. And this module has many more steps. The one in which we are interested in is the HorizonCube well interpolator. And everything that we will do here is will be contained in this single step that needs as input data an HorizonCube. I'll use the HorizonCube. You're just looking at continuous done using 2 horizons, and the well logs. And for the well logs, I'll select my log name as named in all the wells, and I'll select all these wells. And that is more or less all I need to set for the input data. Now you can see that because the guiding of the logs is done using the HorizonCube, it is of utmost importance that these logs are well positioned in the survey area. And the positioning of the logs in the time survey is fully determined by the synthetic to seismic tie quality. Therefore, before you actually can create a good geological model, you have to make sure that the wells are properly tied to the seismic data, are in front of the seismic data. Also, because of this, if you are creating the model straight into the depth domain, you have to be aware that these logs are positioned with respect to their measured depths in the wells, and that most often doesn't correspond to the seismic depths after the preset depth processing. And therefore there may be a mismatch between the seismic depths and the well depths. Now what we need to set up as parameters, well, the first obvious parameter is the vertical extension. None will only create a model in the range of the HorizonCube vertically. And most often, because we are doing gridding, we want to have an estimated log value at all positions of the survey. And the most easy option to use for this purpose is to virtually extend the HorizonCube by assuming that all the layers above the HorizonCube are parallel to the top, and all the layers below the HorizonCube are parallel to the base. The lateral interpolation will be done by an inverse distance weighting as compared to a triangulation. Triangulation is very good for regularly sampled seismic data, which is not the case. When we work with wells, like in this case, we have most often very sparsely sampled data, in which case inverse distance weighting is the method of choice for the lateral grading. Now this step will do a simple grading of, in this case, acoustic impedance logs. And I'm providing now a name for this interpolation step, and I also need to provide a name for the entire volume builder setup. That can be either launched to batch processing by leaving this option on, or what we can do and what we'll do in order to analyze this setup in the first place, I'll toggle off this option and press OK. This will do actually 2 things. This will save the setup on disk, and it will also load this setup in memory for application on the fly on inlines and crossline. Now, if I toggle off the HorizonCube display, we can see that as there is a specific display layer for HorizonCube, you have a specific display kind for volume processing attributes. That's the one I'm about to use now. And you can see that in its right-click menu, it has far less options. Mainly the main option here is to retrieve the setup we've just saved and specified, and to accept it. Now the on-the-fly application is rather quick. It doesn't take so long, 2 or 3 minutes. For this live demo, I'll switch directly to the output. And when you do this kind of processing, you'll get very quickly this kind of output, which is your initial model created in the entire survey area. And actually, this is not the one I've just created. This is an example I've made using a proportional slicing between this base horizon and this top horizon. This corresponds to the standard case, to the standard kind of models you're used to have when using a very limited number of horizons to steer your log values. And this is what I want to compare with the same gridding output when using the HorizonCube as a steering provider, which I display now. And so here you can see, I'll toggle off a few times, the main major difference between a proportional slicing, so the usual impedance model, and the data-driven HorizonCube-driven impedance model. And as you can see in the range of the HorizonCube, we have a much better description of the geology and of the layers that actually honor the geology as compared to the standard case. This will become more obvious if I show at the same time the gridded outputs with some partial transparency on top of the seismic data. Now you can see much better how these impedance layers from in the initial model actually are following the seismic reflectivity. And that is the whole purpose of this exercise. It is the whole purpose of including an HorizonCube as an input to the gridding of the well logs. And actually what has been done for impedance can be repeated for each and every log. So instead of specifying an impedance log, you can simply, well, we can remove all this and add again a porosity log. It could be any quantity stored as a log on your OpendTect wells that is gridded back to a 3D volume. And if I do this for porosity, then you'll get a porosity. This time I've used the other output parameters that to output only porosity values in the range of the HorizonCube, in vertical range of the HorizonCube. But still, so this amplitude corresponds to gridded porosities, and they are following the seismic data just as good as the impedance model. We'll see when I toggle this option off. And now this the creation of the impedance model gives us a very detailed overview of estimated impedances, and most often these impedance models are not used as raw for an impedance inversion, but most interpreters actually will want to low-pass filter the seismic data, the impedance model at the regions of the seismic spectrum where the seismic amplitudes become to have some kind of data. And this workflow is actually done after the gridding of the impedance data using an attribute of kind frequency filtering. And this attribute will input our initial impedance model as steered using the HorizonCube. We'll perform an FFT, a low-pass filtering at, let's say, to start 10-15 Hz. And we'll do some frequency tapering, but no time tapering in in order to avoid having artifacts at the top and tail of the traces. And this attribute we can apply on the fly on a layer to have an overview of the difference between the gridded, this lower gridded output and the same after low-pass filtering. And that's what you can see here. Actually, the amount of filtering can be controlled in a much thinner way by using the evaluate attribute option of the attributes that we know. This was this icon. In this case, I can compute a number of frequency steps, so start frequency for the filtering, compute them on the fly on a specific layer, and then toggle very quickly between these maximum frequency parameters. That's what I'll be about to do in a few minutes, in a few seconds. And when this is loaded on the inline, I'll be able to see the effect of this parameter and to browse very quickly through these maximum frequency. So the maximum frequency here in Earth is displayed. That is this number. We can see that at already 15, 20, 25 Hertz, we have all the gains of the HorizonCube steering grading, and still we have low amount of frequencies in our initial low frequency model this time. And now I can press accept for this parameter and optionally process this data on disk. And that ends my live demo on how to create geological models in OpendTect using the HorizonCube as a steering provider. I'll hand over the presentation to Groot that will go on and present us two other applications of the HorizonCube, respectively the sequence stratigraphy computation and the well correlation panel.